into space. And with modern techniques, we can measure the temperature of the solar corona, and that temperature is in the millions of degrees Kelvin. How can that be? The surface of the sun, what gives us our light and heat, is no hotter than about 5,500 degrees Kelvin. So you have the surface of the sun at 5,500 degrees Kelvin. You have the corona at millions of degrees Kelvin. And we all know from the second law of thermodynamics that you can't heat a hot body from a cooler body. So this is a conundrum. How do you heat the solar corona? Well, you see that the solar corona is dynamic, and so you suspect that maybe the answer is in something dynamic that's happening on the surface of the sun that starts out as kinetic energy or acoustic energy or something else, and then gets translated into thermal energy once it gets out into the corona. But we don't know how that transfer occurs. So this is one of those things that, science can't explain this. Of course, when you get things like science can't explain things, a lot of people take that as a whole indictment of science, right? That science can't explain blah, blah, blah. But to us, scientists, that's a challenge, Science can't explain, we got to figure out how to do this, So one way we think of solving the problem of how to heat the solar corona is to examine the dynamics of the inner corona, which we can't do at a single site in a total solar eclipse. So what's the answer? The answer is to set up a bunch of telescopes all along the path of a total eclipse and record the passage of the moon's shadow all the way along that passage. Because the moon's shadow, the moon travels, see, we can do this math. If you're sitting on the surface of the Earth at the equator, the equator, the circumference of the Earth is what, 25,000 miles, and you have to go around that in 24 hours, so you're moving at 1,000 miles an hour. This is one thing that the flat Earth people don't like, right? Because we can't conceivably be going that fast, but we are. So we're moving at 1,000 miles an hour counterclockwise, looking down from the pole. And the moon is also moving around us in a counterclockwise fashion. But the moon's orbit is 60 times the diameter of the Earth. I think that's right. And it does that traverse in what? A month, 30 days, right? Right? Okay, yeah. Can we work it out in our heads? So the moon is moving at roughly 2,000 miles an hour. We standing on the Earth are moving at 1,000 miles an hour in the same direction. Moon is moving faster. So the moon's shadow is moving across the surface of the Earth at something like 1,200 miles an hour. To cross the continent of the United States, it takes, therefore, something like 90 minutes. The eclipse that we will have in August, just a month from tomorrow, sorry, the 21st, I'm very excited about it. I expect many of us in this room are very excited about it. A month from tomorrow is the first eclipse that crosses the entirety of the United States since 1917. So it's 100 years since we've had an opportunity like this. And of course in 1917 we didn't have the internet, we didn't have fast CCD cameras. There are lots of things we didn't have in 1917 that we have now. So a number of people had this idea, but Matt Penn was the one at the National Solar Observatory in Tucson, was the one who acted upon it. The idea of stationing a bunch of observers with identical equipment at a bunch of sites, 68 it turns out, stretching all the way from Oregon to South Carolina, near the center of the path of totality, with identical equipment. And the equipment, the telescope is not terribly fancy. It's an 80 millimeter diameter, 3.5 inches basically, 500 millimeter focal length. Telescope costs, I don't know, $200 or something like that. The mount costs similar. The magic that makes it all work, however, is a CCD camera like this. This one costs $1,400, so this is by far the most expensive piece of equipment.
Pass that around.
No. This is what it looks like. It's not very big, it's not very heavy, and it's very sensitive, so you don't want to point this naked at the sun, because it will die. So we have to make sure that we shield it whenever we're about to put it on our telescope, and make sure that before we put it on a telescope we have a solar filter in place, blocking out most of the sunlight. So this little camera is capable of taking pictures very, very fast, and via a USB 3 connection, it can download pictures equally fast to a computer. The other trick that we have is this little kludged up box, which consists of an Arduino robotic controller. If you have people, any of you do robotics or have kids who do robotics, they probably have Arduino things, and they may have little robots running around the house doing funny things. This little robotic controller has a GPS antenna, so it's got a GPS thing, so it can give you accurate timing. It also tells you where you are, but that's not going to change from the beginning of your experiment to the other. And this cable here connects to the camera, and this robotic controller then can tell the camera what exposures to take and how frequently and so forth. So we have this all, and then both the camera and this Arduino are connected to the computer by USB cables. And so the idea is that the camera, when during totality, the camera will be taking a sequence of exposures, 8 exposures at a time, varying from 0.4 milliseconds in length to 1.3 seconds in length, so a factor of 3,000 difference in exposure time. Same aperture, just the exposure time differs, in quick succession. And it will do that over and over and over and over again throughout the 2 1/3 minutes of totality that are available to us. So we're going to be using this with the telescope and so forth at a site in central Wyoming. It's Pilot Butte Reservoir is a site that we've chosen. We've selected a group of 8 very talented and enthusiastic high school students to come with us, and they've been training on this equipment. They know how to run the computer, they know how to run the telescope, they understand the basics of the camera. We've been practicing 4 or 5 times already on the sun, the naked sun, of course, because we don't have the moon in front of it. So we keep the solar filter on all the time, but we do this whole sequence. We do calibration flats. Well, first of all, you have to align